Hi, so we're back, and in today's video we're going to be solving this little question here. Um, and you know the book, Shankar, Principles of Quantum Mechanics, Linear Algebra question from Chapter 1, Exercise 1.8.2, and all the stuff. So let's get right into it. We have this beautiful looking matrix over here. The first question is that, is it Hermitian? So we already know what it means to be Hermitian. Okay, what matrices mean by being Hermitian, we have no idea. But we can say that the dagger of this operator is equals to the operator itself. If that is the case, then this is Hermitian, right? So similarly, we have to, and what is dagger? Dagger is just transpose, complex conjugate, or vice versa. And as you can see, this thing, transpose of this is actually 0, 0, 1. God dang it. 1, 0, 0, 0, 1, 0, 0. Which is conveniently, oh my goodness, why is it 2? Which is also the omega over here. So, right. Done. Cool. So what's next? Number 2. The simple find its eigenvalues and eigenvectors. So let's start off by eigenvectors and eigenvalues, because without the eigenvalues we can't figure out the eigenvectors. So yeah, let's do it. So what's the conventional method? We have the okay, you know what? No, I don't even want to write the eigenvector equation right now. We already know that the determinant of the operator minus its eigenvector and its identity gives us 0. And with this, we can figure out the determinant. So for convention's sake, let's just write it like this. Determinant minus omega 0, 1, 0 minus omega 0, 1, 0 minus omega. Why am I saying omega? Oh my goodness. Oh crap. It's lambda. God dang it. God dang it, it's lambda. Man, it's a lambda. And what the fuck was I saying? Anyway. Cool. So guess what? This gives us minus lambda cube plus 1 times plus lambda. And how did we end up with this? It's simple. First, this times this minus this, or well, okay, so I shouldn't have been so cocky, I think. I don't know, let's trace back a bit. So this times this times this gives us minus cube, right? Yes. Minus this is 0. Plus 1 times 0 times 0 is 0. Minus omega minus omega times 1 is omega. So yeah, I was correct actually. That's lucky. I mean, it's kind of a habit for me right now, so like I don't even have to think about it, and it just happens. And my PC fucked up. So let's just write it down like little chads. I don't want to see this minus sign because I hate minus signs. Trust me, I have a lot of issues. So here we do our conventional thing, take lambda as our common factor, and then we have lambda square minus 1 equals 0. So this gives us our lambda, which is first 1. Then we have omega equals to plus minus 1. So yeah, let's just write 1 plus minus. So these are our, oh god, no. Yeah, these are our eigenvalues. Awesome. So, obviously, then we need to figure out the eigenvectors. And how do you figure out the eigenvectors? Well, I'll show you. Well, I showed a lot of things in details in the previous video where I solved exercise 1.8.1, so you guys should check that out if you're there, I guess. But, well, I'm just gonna give a brief, fuck, a brief thing, really? Come on, Josh. Anyway, so for lambda to be 0, we need to find this. What is this? And let's not forget, we need to find the normalized eigenvectors. Uh, normalized. So we have our usual thing, our usual eigenvector equation, and this is 0, and this is a ket, okay? Never forget this. Never. And this one is a bra. Ha ha, some adolescent kid is like, yeah, it's a bra. God dang it, dude. Yeah, I know, even I laughed when I first heard about it. Yeah, so never forget about these two things. These two bracket notations, these are important in quantum mechanics. Really important. So these are our column matrices. Yeah. Ket is like column matrix and bra is row matrix. Please don't make me show you how column matrices look like. God dang it. But I will show you either way because I have to. Yeah, I kind of have to. So for omega equals 0, what is the value? It's 0, 0, 1, 0, 0, 0, and 1, 0, 0. It's like I'm talking to a robot, like a robot, and it's very uncomfortable, and cat gives me v1, v2, and v3. Damn. Wow, that's let's just go on with the tree. Whatever. And this is our column null matrix, or null column matrix, whatever you want to call it. So as you can see, 0 times v1 is 0. This gives us v3 equals to 0. Okay. Then 0 equals to 0 because this. And then v1 equals to 0. So from here, what can we derive? We could say that v2 over here, since v2 doesn't have a specified answer or specified value, we can easily say that v2 is an arbitrary. So if that is the case, that means we could set v2 to whatever we want, and the final normalized eigenvector will be, well, the same. So let's go with v2 equals to 1. And as you can see, we have to fulfill these two conditions, which is like v2 equals to 0 and v1 equals to 0. That means v1 is to be 0 and v3 needs to be 0. And if we want to take the norm, by the way, norm is actually, well, if you want to normalize, that is, norm is the 1 by square root of bra v and ket v, the dot product. This is essentially the dot product. So yeah, you know the drill. Get that stuff in here. So since there isn't a complex value, then bra doesn't really do anything. just transpose this thing. So this gives us 1 square and root, and this is 1. Hence, we have 0, 1, 0. So you might notice that if our value of v2 is, for example, 2, then this becomes 2 and this gives us 1 by 2. So it gets cancelled out. And henceforth, our normalized vector, eigenvector, is this fella right here. This is quite important and this is quite helpful. I'm not going to go into details, but if you are into quantum mechanics and want to learn this stuff and you're trying to go for linear algebra for now, then please do remember this. It is very important and yeah, quite important. So let's go for omega, not omega, lambda equals to 1. So what is this eigenvector? Simple. Similar to the previous one, this is minus 1, this is 0, 1, 0, minus 1, 0, 0, 0, minus 1. Awesome. And we have v1, v2, and v3. And our null matrices. Trust me, trying to LaTeX this kind of stuff is pretty bad. I mean, no, it's not really bad. It's pretty simple. Okay, so I might make a video about LaTeX in the future. I'm not a pro in LaTeX, but it is quite important, and I can do basic LaTeXing. I guess I might make a video about this in the future. But anyway, I digress. So the first row, this gives us v3 minus v1 plus v3, which is equal to 0. And from here, you can probably guess that v3 and v1 must be the same value. And here we have minus v2 equals to 0. Of course, so v2 equals to 0. And I should drink water, but there's no water over here. Fuck my life. Okay, so here v3 is, oh, right. So there needs to be a 1 here. I accidentally did not put that. Apparently? God dang it. Okay, something happened, but I'm not gonna explain it to you people because I'm a fucking dick. Yeah, essentially my copy where I solved this thing, it was a bit wrong, but it doesn't matter. So this gives us 0. Okay, this is 0, and this is 1, this is 1, and its norm gives us quite a bit actually. 1 square plus 1 square is this, and henceforth this gives us 1 by root 2, 1, 0, 1. This is our second bullshit. Oh, sorry about the slurs and curses. I don't really want to do those kind of stuff. I don't want to say this kind of stuff, but like it just happens. I need to solve it. Like literally. I need to fix my mouthing issues or wording issues. So what if it's minus 1, huh? What if the eigenvalue is minus 1? Simple. We do the same fucking thing. You know, it's just messed up. Like, a few seconds ago I said that I have to change my speaking way, if that makes sense. And a few seconds later, I end up saying another slang, or not a slang, it's like slur, curse. So I end up cursing again. God dang it, it's messed up. Okay. If you're still watching this video, I don't even know why. So thank you, I guess. But like you guys are here for learning, and I'm here saying random stuff while solving the problem instead of explaining to you guys why it's going on. But like at this point, you probably get the gist of what is going on. Just put in the values in the eigenvector equation and voila, you have your answer. And I missed a one over here. You see, usually what I do is I talk to myself if I'm not listening to any music. Right now I'm not listening to any music, so I have to talk to make me less distracted. But the paradox is that while I'm doing this, I end up making mistakes because I'm talking to myself, which requires a bit more of your brain than anticipated. So this ends up being a problem in itself. This makes me less distracted, but it's a big problem. So where are we here? Where are we? Now as you can see, our V2 is 0. And these two things, like these two equations, suggest that the two values of V1, the two values V1 and V3, they are different. So we can say -1 and 1, or vice versa, whatever you want to call it, or call them, whatever. And this gives us 1 square plus -1 square equals to 1 by root 2 and -1, 0, 1. Done. Voila. So now the third question. The third question is actually very interesting because diagonalization is also quite important. Well, at least in linear algebra it is. I'm not quite sure about the uh, QM part, but from what I've learned from my peers, it is still quite important. So they asked us to diagonalize this whole thing. Wait, let me check the question. Wow, it's so long. It's very long. Okay, this verify that omega, not omega, uh, u dagger omega u is diagonal, u being the matrix of eigenvectors of omega. So we have to verify that this is a diagonal. What is the dagger of u? U dagger omega u. And this gives us a diagonal matrix D. Okay, we already know that this gives us a diagonal matrix, but still we're gonna solve it like randomly. Now that we know that this thing gives us a diagonal, that should mean that these two things, these two u's, are actually a part of this matrix. And in the question it already says that it is a part of the stuff, the eigenvectors. So u is essentially 1 by 2 times, now this is going to be a bit tricky, all the eigenvectors combined. And it's not addition, might I add. What are our eigenvectors? This one, okay. Then this one, awesome. Then this one, great. So if we combine all of those three things, what we end up with is, god dang it, 0 to 0 root 2, 1, so not 1, oh yeah, just 1, 0, 0, 1, 1, minus 1. Right. So trust me, it's very hard for me to understand it as well. It was and still is. But essentially, you just need to combine these three things, these three eigenvectors, and voila, you have a unitary matrix. And this unitary matrix is very intriguing. Why? I'm not going to tell you people because I am a dick and I don't know it. I need to learn about this a bit more now that I think about it. But for the sake of this video and solving the question, we just need to know that if we combine all of the three eigenvectors, we get a unitary matrix, and if we multiply this with the dagger, let me just tell you this. So U times U dagger is identity matrix, which is also equals to this. You might know about this, you might not, but you should regardless because it's very important. And from what I know, a lot of it is required. Similarly, we have this guy here, the inverse. And you should know about this. We all should. Technically speaking, if a matrix is Hermitian, for example, that guy over there, these three things, these two are like, okay, I kind of messed up, but like, you get the point. This one and this one are equal, okay? Well, not equal, but like similar. And this one is, these are like similarity transformation, and this one is unitary transformation. But we'll not get into that. So where were we? Right. So this is our U. Great. So what is the U dagger? Simple. Let's write it over here. God dang it. U dagger is, like I told you before, is this. But since the values are real, I mean this whole matrix is a real matrix with real numbers, this is just transpose. Oh no. Yeah, this transpose. So this U dagger gives us 0, 1, 1. Yeah, 0, 0 here, and root 2. Okay, this is just messed up. Yeah, root 2. This is 0. This is 1. This is 0. This is minus 1. Finally. Great. Awesome. Amazing. Now, let's go into the meat part, the meat one. So let's just put in the values over here. This is 1 by root 2, 0, root 2, 0, 1, 0, 1, 1, 0, minus 1 times our omega, which is 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, times this guy, which is, man, I'm feeling sleepy right now. Okay, which is 0, 2 root, wait, did I, sorry, yeah, 1, 0, 1, 1, then we have 2 root 2, 0, 0, minus 1, 0, 1. Great. So, since these two guys over here, this one and this one, they are constants. Well, not constants, like simple numbers, scalars, we should say, if we're physics people. So that scalar just gets multiplied, and these two give us, well, 1 by 2. Now we're left with these two people and these two people. Well, there are many ways you could go with it. Conventionally, there are 2 ways. I don't even know for what. But we're just going to multiply this one and this one, then this 2 times this 2. So let's go with these 2 guys over here. These 2 guys over here. So what do we get? This row times this column gives us 0. This column, this row times this column gives us 1. Wow. And this row and this column gives us -1. Great. Similarly, this row and okay, so all of this gives us 0. Cool. And then this row, this column, 0. This thing, 1. This and this 1. Awesome. Times 0, 1, 1. Am I missing something here? I feel like I'm missing something over here. Something very important. Something very important for some reason. No, I'm not. Let's continue. If I do make a mistake, then we can fix it later on. It's like you have to solve like 80% of the math. If it's wrong, then you gotta fix the rest 20%, and that's how things go. Because you're bound to make mistakes, and you just need to go up, and you just need to bounce back up and just learn from your mistakes and stuff. So this one gives us 0. This one gives us 0. Wait, that should not be happening. Oh wait, okay, it does. It should. It's not an identity. I was thinking that it's gonna give us an identity, so yeah, but it's not gonna give us the identity. Anyway, this and this gives us 0. Cool. As long as we don't get anything from this row and this row, we'll be happy. We just need to make the diagonal stuff. So this and this gives us 0. This and this gives us 2. This and this gives us -2. Okay, no, not -2, 0. Finally, this and this gives us 0. This and this gives us 0. This and this gives us shouldn't be 2. Yes, it's -2. Amazing. Yeah. Hence, this gives us 0, 0, 0, 0, 1, 0, 0, 0, -1. This is the diagonal. So they told us to verify that this is a diagram. Sorry, they gave us or told us to figure out or prove that this thing, or I should say this. My God, this is not happening right now. This gives us a diagonal matrix. And yes, we just proved that this is a diagonal matrix. This thing gives us a diagonal matrix. So we are done. And before we're done, I need you people to subscribe to this channel, like what you see, and comment. God damn it. Also, if you have any questions, please do ask me down below, because, well, there are many things we don't understand, you don't understand, I don't understand, so the more we ask questions, the more we learn. So that's about it. Thank you all for watching this video. If you're still here, then damn, kudos to you. Then you must definitely subscribe and give this video a like. And yeah, that's about it. Thanks for watching this video, and I'll see you guys in the next video. Peace out. Goodbye.